Hello, welcome to today's webinar. We will get started in a few minutes. We'll just let people start to come in. While we wait, let me introduce myself. I'm Jessica Finnegan. I'm the Customer Success Manager here at Coreform. And then Wilford, did you want to share the slides while we wait for everyone to pop on? Let's just get the slides up and then, oh, there we go. Once we get all this situated. Okay. Again, welcome to today's webinar. I think everybody's kind of popping in. Today's webinar is about using Cubit, Python to develop OpenFoam case directories. And then we actually have one of our expert Cubit users who works at Omega First, Wilford Smith, is going to be presenting today's webinar. So we're excited to have him. And then I'm Jessica Finnegan, like I said, and then Wilford will introduce himself more fully in a few minutes. But today's agenda will be OpenFoam and Coreform Cubit. And so the agenda will kind of follow, like, just introduce the capabilities of Coreform Cubit and OpenFoam, discuss the background of OpenFoam, including the setup and then input files and what Cubit provides versus what you could do with OpenFoam and Python. And this webinar is really going to be a nice one for beginners because it assumes no experience with OpenFoam, but some familiarity with Cubit. So this is like a perfect webinar for us. And if you're not familiar with Coreform Cubit, we are an advanced meshing software for challenging simulations. We have CAD import. We allow for CAD imports and cleanups. And we're one of the best ways to accelerate just meshing in your, sorry, my dog is barking. While Coreform, if you're also interested in Coreform within your company, Coreform Cubit, please also let us know and we can help you do some consulting work with that. Sorry, the dog is very upset about something. And then if you'd also like to check out our other webinars on our website, please also check those out. We have we do quite a few webinars, so there might be other topics that also are important to your workflow. With that, I'll turn the time over to Wilford.
Okay. Good morning, everybody. My name is Wilford Smith. I am an engineer and a partner in a consulting firm, Omega First, LLC. We do consulting for modeling and simulation with a focus on computational mechanics. I have over 40 years experience performing CFD and reactive flow calculations. In addition to CFD and reactive flows, I've also been involved in nonlinear structures, including large displacement, nonlinear material properties or materials, and then doing explicit dynamics, primarily ODyna 3D, LS-Dyna, and a few other explicit dynamics codes. For the last 10 years, I've been working with using OpenFoam as a CFD solver. And so that's what we're going to talk about today, is using OpenFoam as a CFD solver. Well, first of all, what is OpenFoam? OpenFoam is an outgrowth of a proprietary code, Foam. Foam stands for Field Operation and Manipulation. It was initially developed as a closed source code back in the late 90s, early 2000s, but it was open source in 2004 after the original developers, university in Europe, decided that, well, they went bankrupt and decided to open source the code. What it really is not necessarily a CFD code. It's a sequence of CFD applications and libraries. It's an object-oriented library. It solves, in general, computational physics problems using the finite volume method. They have an extensive array of spatial discretization, and time marching methods that they use. And the idea was that you would take those methods and combine them into an end user developed application. In the process, they developed some internal applications that they would put out there. And uh, over the course of time, they developed enough applications that, in fact, they have a fairly wide range of applications. You don't really have to do a whole heck of a lot of coding to actually use them. So right now, what they have are fluid dynamics application solvers, structural application solvers, EM, electromagnetic application solvers, etc. And I'll show you real quick in a few minutes when we talk about the directory structure of OpenFoam, some of the solvers that are available within the OpenFoam system. Right now, OpenFoam is one of the top 3 most used CFD applications. And it has a large user base, the large number of open literature publications out there. It handles not only small university academic scale problems, but you can actually do some fairly large industrial scale problems also. And in fact, it is trusted by industry and academics. And it's the most important thing from my perspective is it's open source and extendable for each individual's unique situations that are not covered by the large number of included applications. So for example, one of the problems that I've been working on are electrochemistry problems. It turns out that there are no included applications on electrochemistry, but there are some open source OpenFoam applications that have been written. I was able to go out there, find a couple of the applications and modify them to fit my problem. So the next question is, why would I use Coreform Cubit with OpenFoam? The very first thing is OpenFoam is primarily for solving large-scale finite volume problems in computational mechanics. It has some simple grid generation software embedded with it, but if you do anything that's any larger than, say, an axisymmetric nozzle problem or a tank or something like that, anything that's more complicated than a simple geometry, what they have built in is not a viable option for generating the high quality grids that you'll need for solving your problem. Coreform Cubit fills the void by providing for high quality grids and generating high quality grids in the correct format for OpenFoam's polymesh dictionary entry. It works with a large number of 3D modeler formats and making it fairly easy to integrate into the design simulation workflow. It also provides geometry cleanup and simplification, fairly straightforward in both cases. And most importantly, it provides high quality hex elements on complex 3D assemblies. Even though OpenFoam allows for different types of elements in addition to hex elements, it has tetrahedrals, it has multi-sided polyhedrals and things like that. For the most part, I've always used text or hexes, and OpenFoam does a nice job generating those hex elements for me. Okay, a little bit more background on OpenFoam. Right now, there are at least 2 versions of OpenFoam that trace back to that original version 1 back in 2004. There is the OpenFoam.org distribution. It's distributed by the OpenFoam Foundation, and it was predominantly developed by contributors from CFD Direct. OpenFoam.com is the second distribution. It's primarily distributed by OpenCFD Limited, and it's mostly developed by ESI OpenCFD. The 2 versions are essentially the same, but they have 1 different release schedules and then 2 different versioning protocols. So for example, OpenFoam.org versions are sequentially numbered, with the current release being version 10. Whereas OpenFoam.com versions use a year-month numbering with approximately 6-month release cycle between them. So the current release right now is version 2212. That means that it was released back in December of last year. There should be an update coming soon. That would be something, and the version number would be version 2306, preferred if they get it out by the end of this month, or whatever the month is they would actually release it, that XX. As far as installation, OpenFoam is available natively on most flavors of the Linux and on Mac OS. And as we'll talk about here, with using the Windows subsystem for Linux, it's available under Windows machines. Ubuntu is probably the most commonly distributed version of OpenFoam, and they maintain at least 2 to 3 years worth of Linux versions, or at least 2 to 3 versions of Ubuntu going back. I think their long-term solution right now is 20.04 Linux, and of course the most recent version of Ubuntu. For Windows machines, the easiest way to install OpenFoam is using the Windows subsystem for Linux, a WSL. It's a fairly straightforward install of WSL and Ubuntu, or on any other Linux platform using Microsoft Store. So for example, just go out to the Microsoft Store, you do a search on Ubuntu, and you install it, and it will install WSL, it will install Ubuntu, and you'll have a working version of both on your machine. And what it provides for is a full Linux running mostly seamlessly alongside Windows, so that you can seamlessly access Windows files from within Linux. And similarly, you can access Linux files from within Windows. So once you've installed WSL, and you can then follow the instructions for Ubuntu, or whatever variant of Linux you have installed with WSL, using the instructions given down here at this location. Again, that's the openfoam.org distribution of OpenFoam. My installation, I've got a couple. I generally keep both versions on my machine. So I have WSL with Ubuntu 20.04 on my machine as my WSL version. I have, what we'll talk about today is the openfoam.org version 10 that I run in WSL. And then I have all of my pre and post processing I do on the Windows side of the machine. So for example, I'm running Coreform Cubit 2022.11 on the Windows platform. Same thing with ParaView as my post processor. I'm running 5.11 version of ParaView, and then a Visual Studio Code or Notepad++ as my text editor. Because one of the things that you'll end up with OpenFoam is there are a lot of text files you got to work with, or a number of text files you need to work with to get it to go running and stuff. Okay, next wanted to talk to you really quickly about the workflow using OpenFoam. If you want to do a simulation in OpenFoam, the very first thing you have to do is figure out what physics are involved in your problem. Like I said, OpenFoam has a number of, in fact, over 50 application solvers that include different physics. You can go from a compressible flow, incompressible flow, multi-phase flows, reacting flows, etc. Each application area, there are tutorials and examples. What I would advise you to do is to use those tutorials and never start from scratch. Let me give you a quick example. I'll go through and walk you through the directory structure. Okay, so for example, I'm in the web.
We can't see that screen yet.
You can't see that screen
No.
yet? Okay, let me do this real quick. Share screen. Okay, can you see my screen now? Yes.
Yep.
Okay, fantastic. Okay, so this is just my directory. Again, I'm in the Windows system right now, looking at the directory structure under Windows. Where OpenFoam would be installed at. As you can see, I've got OpenFoam going back to OpenFoam 8 and their latest OpenFoam development version. For right now, we're worried about OpenFoam 10. These are all the application areas that OpenFoam has. So for example, there's a basic, which is just an introductory. It has some potential solvers, some Laplacian solvers, and some scalar transport calculators. There are combustion calculators in there. One is just a straight up chemistry calculator, a reacting foam, which essentially is a reacting flow, including all the Navier-Stokes terms that you would, incompressible reacting flow. Compressible flows. There are 3 different versions there. So for example, the row central foam, it is a modern TBD compressible flow solver for strong shock waves. The pimple foam and simple foam are more aligned along for doing compressible low Mach number flows, so up to around Mach 2 or so, with shock waves included, and so on. So for example, compressible and electromagnetics, heat transfer, and compressible flows, and so on. So, but, okay. And within each one of those, there are tutorials. And these are fairly important because even though the documentation for OpenFoam is fairly extensive, there is still a lot of work to be done to actually generate a case and get a good running calculation out of OpenFoam. So for example, if I were doing a calculation that involved a compressible flow that I wanted to do at a high Mach number, instead of me starting from scratch, what I would do is go to the tutorials under compressible flows and use the central solver, and then pick one of these as to start with. And what would generally happen is, if I go back and look at OpenFoam, what it does is it generates a case structure that includes a system directory that I have to populate and a constant directory, which I have to populate. These are text files that have to be populated using the OpenFoam system or whatever system that you have available to you. Okay. So. Now to make sure, do you see my view graphs now again?
Yeah, we're back on the slides.
Okay, fantastic. Okay, so now, again, the simulation workflow. We used, as I said, I'll use an included tutorial as a starting point for my simulations, no matter what. Like I said, there are a number of starting points or tutorials out there. Each application solver that's included with OpenFoam has at least one example using the application solver. So when I start a new problem, first thing is to find a fully worked example that uses the solver for the problem. Once I've got the problem set up, then the next thing is to develop the geometry. And what I would generally do is use a solid modeling tool such as FreeCAD to do that, or SolidWorks or whatever, and save those out as either a step file or a ACIS file. And then, or I can directly within OpenFoam use block mesh or snappy hex mesh. Those are fairly rudimentary text-based grid generation tools that, again, if you're trying to do anything complicated, I wouldn't advise that. And then, of course, Coreform Cubit. It allows me to do not only the geometry development, but also the grid generation aspects. Then I have to identify my boundary and initial conditions. my materials and properties, and then finally generate the grid using the Cubit or OpenFoam. So let's go back out here. That's not good. And pick up again. So can you see my Cubit screen now?
Yep.
Okay, fantastic. So within Cubit, I put together a very simple block that we're going to be going through and doing, at least showing you how to generate a grid from here using Cubit, and how that grid is then transferred into OpenFoam. So this is a basic block that's built up in Cubit from Cubit commands. And what it does for me, what I wanted to do here was just to do a forward-facing step and a supersonic flow. So I started my simulation using a tutorial that was in the row central poem directory, the forward-facing step problem. And within Cubit, it has over in on the far right panel, in the command panel, you can set up your boundary conditions and initial conditions for a CFD calculation. It includes a number of various boundary conditions that you can put in there. And what it does for you when you install the boundary conditions, it, for example, creates the OpenFoam commands needed to implement that boundary condition. So for example, if I were going to do an outflow condition, then I can name the outflow condition. Let's say outlet and select the surface that I want to make it on, and then apply it. And what it does for me, it gives me that outflow condition that now is written out to the file. If I then go over, I've got my grid, I generated my grid. I can then go and save that out or export it to an OpenFoam directory. And what I'll put it in is and what it should have done is create one part of the simulation that I would need. So for example, go back up. Here. It produces, in the constant directory here, it produces this file structure from that file. This is one that I've already generated. It produces a boundary condition file for me. And in there, all the faces that I need, all the neighbor points, all the owner points, and all the points that are included. One of the problems with OpenFoam is, unlike with conventional FEA analysis, where generating a grid generally only means I generate my nodal points and then the connectivity between the nodal points, and that gets me my grid. So for every, I discretize my system doing that. The finite volume method, at least as implemented in OpenFoam, you have to generate not only the nodal points, you generate faces, you generate neighbor faces, and you generate an owner set of owner faces. So the grid generation can get fairly complicated within OpenFoam. Additionally, what Cubit does, it generates this file, that polymesh file. Everything else I have to generate on my own. So for example, momentum transport, what that is is it tells me what kind of simulation I want to run, whether I want to do a laminar flow, turbulent flow, and then if I'm doing a turbulent flow, how I'm going to treat that turbulent flow. What are my turbulent equations going to be, whether it's a K epsilon or omega, K omega simulation. Okay. Also have to generate my physical properties. And in that file, it tells me the thermodynamics I'm going to include in there, how I'm going to treat the mixture, my transport properties, whether they're constant, whether I'm going to use a Southern unknown, or for example, and then the equation of state, whether it's a perfect gas, real gas, equation of state, and the species that I might be interested in following through, and the energy equation. So this is one of the reasons that I say you never start from scratch, just because of the number of files you have to generate manually and some of the various properties you have to put in there. So if you start, as I said, I started from a simulation that was done with the forward-facing step in the particular application that I wanted to run, and then just modified from that point. So for example, for that forward-facing step, we put in a fake molecular weight so that I can normalize my velocities between 0 and 1, or between 0 and whatever, so that 1 is a Mach number of 1, a velocity of 1, essentially becomes my Mach number. My thermodynamics and my transport properties are then pulled together for my viscosity 0. So I wanted to do an inviscid calculation and a Prandtl number of 1. So no heat transfer calculation in that particular case. Okay. In addition to that file, those files which are in the constant properties, I also have to generate a system directory, which basically describes how I'm going to do the simulation. There are 3 files generally within that system directory: a control dictionary, which tells OpenFoam what I want to do and how I want to go about doing it. So it tells which application I want to run, in this case, that row central foam, how I'm going to start. So I can start from the start time, and which is 0 in this case, or I can start from any time. If I wanted to continue a run, I could start at some other time that is in the set of simulations that I've done so far. In all OpenFoam cases, they allow some form of macro substitution. So for example, start time here is really a macro that we generate called start time. When I want to stop, end time is again a macro that I generate, and delta t, and so on. So basically, this gives me an idea of how I'm going to run that simulation. My time simulation, how I'm going to print it out. It just gives me the overall dynamics of running that calculation, including things like a Courant number that I want to run at, a delta t that I want to run through, and whether I'm going to write it out in ASCII format or in or what have you. Okay. And then finally, these 2 tell me, the finite volume schemes that I'm going to be using for doing the simulation. One of them tells me the finite volume schemes, that's FV schemes. And what I have to do is tell it the flux scheme I want to use. And by flux scheme, if you're familiar, if you're familiar with solutions of the Euler equations, or with the full finite element equation, the full Navier-Stokes equations, then it just tells me how I'm going to treat the flux terms on the left-hand side of the equations of motion. So in this case, I'm using a Kuganov method for treating those. How I'm going to time march again, an Euler time marching scheme. And then each of the different terms in the Navier-Stokes equations or in the CFD equations to tell it how I'm going to treat each of the different schemes. So for example, my gradient terms in there, I have to tell it how I want to treat the gradients, how I want to treat my divergence terms, and how I want to treat my Laplacian terms. And again, how I'm going to do my interpolation schemes. Again, if I am doing a finite volume calculation of compressible Navier-Stokes equations, I've got to worry about going from cell centers to cell faces for doing the solution. These interpolation schemes tell me how I'm going to do that interpolation from cell centers to cell faces, and how I'm going to do my limiting terms in there. So for example, that reconstruction, Van Leer reconstruction means that I'm going to go ahead and limit using a Van Leer technique, and I'm going to do a linear interpolation from cell center to cell faces for solving my grouping problem. Okay. So, and then finally, the last file I have to worry about generating is that FD solution file. And what that is, turns out, tells me how I'm going to do my linear solutions within the simulation. If you know, I've got to convert my nonlinear PDEs into nonlinear algebraic equations. And this file tells me how I solve those nonlinear algebraic equations. So for example, I'm going to solve my rho u, rho e diagonally. So it's a diagonal solver, Euler solution, diagonal solver. And then each one of these tells me how I'm going to solve each of the different equations of motion. U are my momentum equations and how I'm going to solve those. And then H is my energy equation. Okay. And, H is my time step and how I'm going to call for my convergence on the energy equation, and the tolerance and the relative tolerance I'll be using on those. And then finally, we go back to here. So once I've set up those, like I said, at the top level, my case directory, I have my system directory. I'm sorry about that. Top level, I have my system directory. That includes my control dictionary. And again, the control dictionary tells me how I'm going to solve that problem, my output IO for the problem, and all that. My finite volume schemes and my finite volume solution schemes. So the FV schemes tell me how I want to treat my various terms in the differential equation. My FV solution scheme tells me how I'm going to solve the algebraic part of the equation set, how I'm going to solve the reduced algebraic solutions. And then within the constant part subdirectory, I have my properties, and the properties are the thermomechanical properties that I have for the simulation and what have you, and my polymesh. Polymesh is what Cubit does for me. And that's a big part of what I need to get done, okay? Is it gives me my grid and all the relevant points that I need in the grid, including my points, point directories, my faces, my owners, neighbors, and the boundary conditions that I want to install on there. And then finally, it also contains all the time directories. As I'm performing the solution, OpenFoam will print out a full set of calculations, and let me bring up. Within there, each one of these dot numbered files is a solution of the equation set at a specific time. So for the initial time, I have to tell it what my pressures, temperatures, and velocities are. Those are 3 files that I have to generate up front. They're generally fairly straightforward to generate. but again, something that I have to tell it to generate. OpenFoam has its own way of doing units. I have to tell it the dimensions of every problem that I put in there. So for example, my object in this case is my pressure field. I can tell it what the dimensions of that pressure field are. And it's working in SI units. Each one of these, I can't remember exactly, but the first unit is a mass unit, second unit is time, and so on. Okay. It's an internal field, and I can tell it that it's going to be a uniform internal field, and I'm going to use a pressure value of 1. And then each of the different boundaries that I have defined within my Cubit geometry generation, I have to go through and tell it what each one of those types is. So I defined something called an inlet on a boundary. With that inlet, I tell it what type of value it is. And for this case, it's a fixed value, fixed pressure value. And I want to have a uniform value of 1 over the whole field, over that boundary. I'll also define an outlet type in my Cubit boundary condition definitions. I have to tell it what type it is. And for this outlet, just do a 0 gradient. The same thing happens on each of the different parts of the boundary that I have defined within the within my Cubit geometry definition. I have to do the same thing for the temperature. In this case, it's a compressible flow. So if I'm doing compressible flows, not only do I solve the momentum equation, I have to solve the energy equation. Energy equation is the temperature. And so I have to tell it how that temperature is distributed both internally, initially, and on the boundaries initially. Okay. The same thing, I defined an inlet condition, I defined an outlet condition within Cubit, and I defined all these various tops, bottoms on the Cubit. Within the Cubit itself, it printed out, when it printed out the geometry and the mesh, it named these, the patches that were on these parts of the boundary. And now I have to go back in there and tell it what those patches actually have. Okay, and then finally, the velocity. And within the velocity, I tell it again what the object is and the dimensions of it. And in this case, since I've got the velocity is a vector field, and I tell it that here with that class, that's a volumetric vector field, I've got to give it 3 values of the velocity. So there is the x component, y component, and z component of the velocity field. And the same thing happens. I have to tell it on every boundary what the value is on that boundary. So for example, on the inlet, I've got a uniform velocity of 3, and 0 and 0 on the velocity. And with that uniform velocity of 3, in this case, if you'll recall, we put in a very large molecular weight so that our Mach number essentially became our velocity. And so what I'm actually telling it is I want an inlet Mach number of about 3 in that case. Okay. And each one of these is a time. And if I go back and look at any of those, then what I've got is, again, a pressure field that shows me what the pressure is at any given time at that particular time. In this case, it's at 12.5 seconds, I think, or at 15.9 seconds, and the pressure. And these are the values of the pressure at the various locations within the simulation. Now, as I said, what I would normally do is run the calculation within the Linux partition, and then do my pre-processing and post-processing within the Windows partition. So I've got, and I showed that we pulled in Cubit in the Windows partition and generated our grid, generated our boundary conditions within within Windows. I also have to do ParaView, which is my post processor, and I've done that within Windows also. So in this case, what I did was I pulled the information back in from the Linux partition, and then just pulled it in and ran it under Windows and got the calculation done. This is at the very end of the simulation. I didn't run it all the way through, but this is at the very end. It's essentially a 2D simulation that I did in 3D. In general, you can run 2D simulations within and 1D simulations within OpenFoam. But what you have to do is either you can run them with zero gradients on both the front and the back side to simulate a 2D problem, or there are some special boundary conditions that you can apply to make it look like a 2D problem. But every problem within OpenFoam is actually is run as a 3D problem. What you have to do is you have to manually tell it, hey, this is going to be 2D, and the way you manually tell it that it's a 2D problem is use those special boundary conditions. And the same thing happens with an axisymmetric problem. If you really want to do an axisymmetric calculation, it's run as a 3D problem, but now you have to put in a boundary conditions on the front and back surface that tell it, hey, even though it is running as 3D, this wedge boundary condition says you only have to look at one sector, and that one sector is the axisymmetric sector. Okay, so I won't walk through using ParaView for your visualization, but it's fairly simple. The one thing I will tell you though is, as I said, I like to run everything within Linux and then do my post-processing within Windows. I can actually, within the WSL ecosystem, I can actually go over to my Windows partition and run calculations on the Windows partition from Linux. So for example, I know that if I go to Mount and D, that what I'm actually looking at, that gets me into my Windows partition right there. That my D drive is actually my data drive under my Windows, under Windows. And so if I want to run a calculation, what I would normally do, set it up in under Windows, leave it in my Windows partition, and then move over to my Windows partition from Linux and run it from there. So for example, here, all of these are run from my Linux partition. There's that directory called run, and this is where all those calculations will run and performed at. Well, and so, and there is that one directory called VTK, which is where all of the output files are. So for example, these directories here are the baseline directories that contain OpenFoam formatted output. And that VTK contains all the directories that are compatible with the ParaView post-processing. So now I can go in and directly pull up ParaView and pull in each of those calculations and do my post-processing. So as I said, I do everything as much as possible in Windows just because I use Windows for everything. For the most part, that is my day, is using Windows. When I want to run a calculation, I want to run it in Linux, and I want to be as seamless as possible once I've run the calculation, once I set it up. So I said, okay, I'll do most of my most of my processing in Windows with a little bit, all of my heavy duty number crunching in Linux, but again, using my Windows partition. So, um, and, and now, and I think that is where I am. Like I said, this has been a very high level intro to using Cubit and OpenFoam. As I said, OpenFoam is a complex system. There are a lot of ins and outs to using it. Coreform Cubit reels in some of that complexity, primarily in the setting up of the boundary conditions and the setting up of the grid itself. Without something like a Coreform Cubit, you won't be able to do very large scale problems. You can do academic problems using the grid generation capabilities that are built into OpenFoam. But if you want to do any kind of industrial scale calculation, you have to control that complexity, and you control complexity using Coreform Cubit. The combination allows the user to analyze complex multidisciplinary engineering problems. As I said, one of the nice things about OpenFoam is it gives you a lot of freedom to go ahead and modify and do other problems. There are 80 some odd over 50 to somewhere between 50 and 80 application areas that OpenFoam natively solves for you, comes out of the box and you can use it for. But there's always that unique situation where OpenFoam doesn't have any capability, and you've got to figure out how to do it. The nice thing about OpenFoam is it's really a library of tools. You can go ahead and put together your own small system and run it. And I've had to do that a few times. Like I said, I was doing an electrochemistry problem, didn't have an electrochemistry solver in OpenFoam. So went out to the internet, found something that was close, modified it, used it for my problem. The most important thing about using OpenFoam is be patient. Get comfortable with using the extensive OpenFoam user community. There is an extensive one out there. And use that community and use the tutorials. The community is fairly easy to get along with. They'll answer your questions and they'll help you walk through some of your issues. And then, like I said, the tutorials. Those are lifesavers, and they can save you so much time because now you don't have to go through and try to figure out how to use a solver. There is someone who's actually used that solver, and now all you have to do is modify the input file for that particular solver. Anyway, Omega first, we're available for OpenFoam consulting. Again, my name is Wilford Smith. That's my contact information. You can reach me on my cell phone, or you can email me if you have any questions. And for now, if you have any questions, be happy to answer anything that you might have.
Thank you, Wilford. That was great. Okay, we have one question. Okay, I'll read it out. The case you have shown is very simple and can be easily obtained. Do you have any suggestions on how to achieve a meshing strategy in Cubit? Sorry, let me go back. One of the most critical issues when dealing with CFD meshing for LES and DDES is to be able to encapsulate the boundary layer refinement via an O-grid strategy. Do you have any suggestions on how to achieve such a meshing strategy in Cubit?
Yes, it turns out that it's fairly straightforward to do that in Cubit. Let me do one thing for you real quick. Within Cubit, I'll open it up again and close that down. There is when you're doing meshing within Cubit, there is that right there. And that is a boundary layer. It allows you to create a boundary layer within Cubit. And so now what you can do is go in there and identify which walls need to have boundary layers attached to them and attach those. And it will give you the flexibility of putting in a fine grid that sort of grows away from that boundary, okay? So does that answer your question?
If that doesn't answer your question, just feel free to type a follow-up into the Q&A too.
Okay.
He asked, somebody asked, are there hardware requirements?
Really? I mean, yeah, there are. What I would think is that, um, you know, for me, I use my laptop. It has a GPU on it. I have an NVIDIA GPU on my laptop, and I'll use that NVIDIA GPU every now and then. It'll fall back in there. But for the most part, I've got a Core i9 that has, I think, like 8 or 9 processing units on it. Uh, and what you really want to have is a lot of memory. So, for example, my machine that I'm running on usually has somewhere between 32 and 64 gigabytes of memory available to me. So if I'm running a large problem, I really do need a lot of memory to do it with. Okay.
We have a few more questions. Do you find any limitations on different element types? For example, is OpenFoam limited to block or hex?
In their documentation, they talk about using only block. The highest order element they talk to within their documentation is blocks, hex elements. But they also do, you can go from a hex to a wedge to tets and things like that. But no, I haven't seen or I haven't worked with some of their polyhedral meshes or whatever. Because, for example, I know that Fluent has a polyhedral meshing capability. I haven't really used any of that.
And then how does Cubit handle complex geometries? For example, boundary layer generation for high Reynolds flow simulations. Do you have examples of such grids?
I don't have any on my machine here, but I do have examples of using those. And again, the way you handle it is you go in, you identify the boundary, and you put in a boundary layer. And that boundary layer you are then allowed to grow from the wall that you put it in on. So for example, you can tell it that I want to transition from the boundary to the main core flow, and say 3 layers, 4 layers, and it will generate those 4 layers for you. It will generate that boundary conditions and boundary layer for you.
And then we have one question. They're wondering if you could show Python as an example, like how you'd use Python scripting.
Yeah, I'm sorry about that. I meant to do that, but one of the problems is just getting everybody up and going. But one of the things that you can do within Cubit is they have a fairly powerful Python interpreter built in to the system. And so what I would generally do here is encapsulate. So for example, copy my history block. And well, actually I think I do have let me do this for you real quick and see if I can find it. And I don't. Well, when I set this problem up, I usually would capture my history. So, for example, within OpenFoam or within Cubit, down at the very bottom, you see that they have the Python. I can input the Python. I can input regular command structure in the errors, but there's this history that shows me all the things that I've done within the editor or within Python or within Cubit over the course of the simulation, the generation. What I can do is just copy that and go to my journal editor and insert it and convert it into Python. And then from there, once I've got it converted into Python, I can then go through and, for example, if I were saving this, when I did that export right there, I can rename that export to to make it look like it's part of my full case structure. So for example, if I'm running in the run directory, I can actually put in the rest of that run directory. So what is it? For example, and so on. And then rerun that from the command line, either from the command line or from Cubit itself, run that. I can also put in just whatever I want to as far as simplifying and moving files around within the Cubit, within Python. So using the full power of Python within the within Cubit and at the command line. Again, doing graphically capturing whatever I need in the history, and then converting it to Python, and then running the Python script.
And then somebody, just a follow-up to the Python question. Do you know if it's possible to run Python scripts in Cubit with higher level, such as like models with varying dimensions? Would that be possible?
Yeah, it should be possible. Okay. Yeah. And then I saw the question about a moving sliding mesh.
Right.
And that depends. As I said, that there's a break in OpenFoam. There's the openfoam.org and openfoam.com. They both have versions of moving grids, overset grids, and moving sliding grids and stuff. So there is that possibility. You can always use that. What I found, I was doing a problem a few years ago where I was looking at a internal ballistics calculation, and openfoam.org didn't have an overset grid at the time. They do now, but openfoam.com did. And so I just moved over and used the openfoam.com simulator to do the calculation with. But again, they are slightly different. The two, if I can't find it, the problem that I want to solve in one of the branches, generally it'll be in the other branch, or I can always go out there and find it online. So the nice thing about OpenFoam is that there's a large user community. Somebody has done something fairly similar to what I want to get accomplished in most cases. I can go back and look at their problem and look at how they solved it and use that information for my problem. And I see that OpenFoam, there's another question out there about the native mesh importer, like fluent.mesh file. And what I would say there is that one of the nice things about Cubit is that it allows you to create natively the mesh file for OpenFoam. So if you're converting from a Fluent mesh, generally you have to have Fluent on your machine. You've got to have Fluent or something on that order on the machine. And so you've got a few different ways of going about doing that. And the problem is if you're using Fluent, then generally you've invested in all the Fluent simulation training. So you've got their mesher and you've got Fluent itself. The nice thing about Cubit is it also generates grids for Fluent. It generates grids for OpenFoam. It generates grids for a number of different application packages. So that's what I would say. Yeah, you can use, and in fact, there are other grid generators that you can use for OpenFoam. Gmesh is one. Gmesh, again, it's fairly simple. It doesn't give you the flexibility that Cubit does, especially on the cleaning up your geometry. If you're getting something back from, for example, SolidWorks, and you convert that to a step file or a SAT file, you're going to always run into small problems, either small slivers, things that aren't just quite right that you have to fix. And Cubit gives you that opportunity to fix those problems and generate the mesh once you got them fixed. So, and that's it.
Well, thank you. And thank you everybody for coming. And we will send out this recording this afternoon, and we'll also place it on YouTube and on our website, so you can rewatch it. Thank you again, Wilford. This was great.
Okay, thank you. Well, take care.